Hello everyone, and welcome to session 2 of our webinar, AI at the Edge, a practical introduction to Maxim Integrated's MAX78000 AI Accelerator, brought to you by Maxim Integrated and EBV Electronic. As with yesterday, your presenters are myself, Chris Artis. I run the microcontroller business at Maxim Integrated. We also have Robert Muxel, who is our system architect for the AI products, and Sean Brooks, who's on the applications engineering team supporting the AI products. Real quick, I just want to recap what happened in the first session. In case you're coming in new to this, there was a previous session that really focused a little bit more on getting oriented with the tools and documentation, and talked more about training models to run on the MAX78000. We went through an overview of the part. We explored the documentation repository on GitHub. We talked about recommendations for setting up a machine learning training system. We talked about some of the demo models that come along in our evaluation kit. We also went through actually training our keyword spotter demo with all the tools and documentation that are available on the GitHub site. And we talked a little bit more about further topics in deep learning training. So on to session 2, we're going to transition to talk much more about the embedded side. We need to bridge that gap between the machine learning side that we talked much more about yesterday and actual embedded development with AI. And so we're going to do that largely through examples that we're going to work on with this MAX78000 Feather development board. So we'll start with a walkthrough of that board. This board is very available through distribution partners, through our website. And it's pretty cost effective, so you can get your hands on one pretty easily. After we go through the development board, we will go through the synthesis directory that's in GitHub and talk about some of the examples there, a continuation really of the machine learning examples we talked about yesterday. And then we'll spend a lot of time on the synthesis step, taking those trained models and converting them to something that will run on silicon, run on the MAX78000. Once we've done that step, we'll go into the traditional embedded development tools, the Eclipse toolchain, and we'll show getting those examples, that keyword spotter up and running. And we'll also talk a little bit about performance measurement, measuring energy and measuring latency, which are really key aspects that the MAX78000 is trying to address for the AI market. And with that, we'll start with a walkthrough of the Feather board from Sean.
So here we have the MAX78000 Feather board. This board provides a low-cost platform for exploring ultra-low power hardware accelerated AI features of the MAX78000 microcontroller. It features an audio codec to enable voice recognition models, such as keyword spotting, as well as a VGA color camera for imaging applications like face identification. So I'm just going to go around the board and point out some of the major components. First, we have a pair of stereo audio jacks. One is for a microphone input and the other is for a speaker output. These interface with the MAX9867 stereo codec, which funnels audio data to and from the MAX78000 via an I2S bus. The MAX9867 has internal amplifiers which allow direct connection of standard headsets and other audio equipment. Here we have an OVM7692 color VGA camera which enables AI vision applications. The camera emits RGB 565 image data to the MAX78000. Be aware that out of the box, the lens of the camera may be covered by a small semi-transparent protective film, and you'll want to make sure that's gone before running the camera demos. Moving left, we have the MAX32625 MCU that serves as a DAP-Link debugger for the Cortex M4F core and the MAX78000. The debugger exposes a DAP-Link interface, flash drive interface, and a UART interface on this USB port. This header is used to debug the RISC-V core in the MAX78000. You can connect an external adapter such as an Olimex to debug the RISC-V core. Here we have the MAX20303 PMIC, which provides power to the board and manages an optional external lithium battery you can attach to this connector. The PMIC has an internal battery level measurement circuit which can be accessed via I2C for the MAX78000. The board also has several buttons. These two are general purpose buttons available via GPIO. They are debounced by a MAX6817. This button controls firmware update of the debugger MCU. In the rare event that you need to update the debugger's firmware, all you have to do is press and hold this button and apply power via the USB. A flash drive called maintenance will appear on your host, and you can use that to drag and drop a firmware binary. This button resets the MAX78000, and this button is a power button which is accessible by the MAX78000 via I2C. Pressing and holding this button for 12 seconds will cause the PMIC to power off the board, and then pressing it again while it's powered off will immediately power the board back up. These two unpopulated headers break out various signals on the MAX78000 according to the Adafruit Featherboard standard, and you probably can't see it on the camera, but the silkscreen labels each of the signals. If we flip the board over, you can see we have a SD card connector here, and over here is a 1 megabit SRAM. Both of these are serviced by a quad SPI port on the MAX78000. You'll notice this inductor and adjacent IC here. This is a buck converter that feeds the MAX78000's vCore A rail. This can be programmatically turned on when the convolutional neural network in the MAX78000 runs models that require more power than the internal supply can deliver. Earlier in the presentation, we talked about network training. The output of training is a set of network-dependent weights. Now we need to use that as an input to the synthesis process. Synthesis is the process of quantizing weights into a form usable by the MAX78000 CNN in the context of a defined network configuration. The ultimate output of synthesis is a set of machine-generated C files that can be included in your embedded C project. So with that in mind, let's take a look at the synthesis repo. First, let me bring your attention to the bash scripts in this directory. You'll remember that we used the GenDemo's MAX78000 script to verify our install previously. The real function of the GenDemo's script is to generate compilable C projects using pre-quantized data located in the training directory, which we'll look at in a minute. Let's take a closer look at GenDemos. Here you see that GenDemos simply calls the AIXI's Python script for each of the pre-trained demonstration projects. AIXI's is really the workhorse in the synthesis process. There are many options which are detailed in the README MD file, but the main aspects you'll want to be aware of is the checkpoint input file and the network configuration YAML file. The checkpoint file contains the quantized weights for the network, and the configuration file contains the YAML description of the network which corresponds to the model used during training. The AIXIzer uses these to generate a C project which gets located according to other options shown here, but essentially it's a relative path into the SDK submodule. Let's take a quick look at where you can find that directory. So from the root of the synthesis directory, we can navigate into the SDK, which is a Git submodule that contains all the C files you'll need to use the MAX78000. It has peripheral code, SYMSYS code, and various project examples. Let's path down into the directory where the GenDemos places the auto-generated C code. Now this directory contains several subdirectories, one for each demonstration. Some of these are created by the GenDemos script, but others are not. First, let me point out the projects that GenDemos can create and update. We have MNIST-RISC-V. This is a version of MNIST that is targeted at the RISC-V core. Next we have MNIST, which you're familiar with from earlier discussions, and this one targets the Cortex core. The other projects you're going to be familiar from previous discussions as well. We have KWS-20, which is the keyword spotter. We have Face ID, and then we have CFAR10 and CFAR100, and finally cats and dogs. You'll also notice there's a common code directory here that just contains a little bit of boilerplate common to all the projects. So these directories get created by the GenDemo script. If you run the script again, the contents of these directories will get overwritten, which is important to remember if you choose to do your C development work in these subdirectories. Generally, you'll want to do your traditional C development work in another directory, or at least avoid modifying the C files generated by the Exciser Python script. There are a few other directories in here that contain demos that add platform-specific functionality to the CNN-specific auto-generated C code. They are Cats Dogs Demos, and this one uses the camera to provide live images as opposed to known answer test, which is what Cats Dogs CHW does. We have the Face ID demo, which also uses live camera images. And then we have the Face ID _ EV-Kit, which uses hardware specific to the EV-Kit that's not on the Feather. There's KWS-20 _ demo, which uses the hardware that exists both on the Feather and the EV-Kit. We have MNIST-streaming, which is a CNN streaming mode example. And finally, we have the Snake Game demo, which only runs on the EV-Kit. An important concept to keep in mind is the AI Exciser Python script, which underlies the GenDemo script, doesn't know much about your target platform. It mostly only generates C code that is specific to the CNN accelerator inside the MAX78000. It's up to you to feed the network with real-world data and do something with the output. To facilitate this, the general approach is to add platform-specific C modules around what the AI Exciser gives you. What you add will be specific to your hardware. Now, I happen to have a compiler installed on this system, so I can CD into one of these projects and type make, and the resulting F file is all I need in order to flash the chip. You can also see that we have a .c project and a .project file, which will allow you to import this directory into your Eclipse workspace and compile and debug from Eclipse. I'll show you how to do this later. For now, let's wrap up our tour of the synthesis repo by pathing back to the root. So we just drilled down on the GenDemo script. Now let's take a look at the other bash scripts. You can see that we have several scripts with the quantize prefix, one of them for each demo. Let's cat MNIST. You can see it's pretty simple. It just calls the Python script called quantize.py. Quantize.py is another heavy lifter in the synthesis toolkit. It's what drives the process of quantizing floating point weights into lower resolution, often 8-bit weights, but it's also possible to specify 4 and even 1-bit weights. Quantize.py takes an unquantized input, which is the result of training, and converts it to a quantized output according to the parameters it's given. Most significantly, the network definition YAML file. The readme.md file in this directory provides full details on this command, but the basic idea with quantize.py is to generate something that AIExciser.py can use to generate a compilable C project. Finally, let me point out a few of the more important subdirectories here. The networks directory contains all the YAML network descriptions for each model associated with each demo. The train directory contains both quantized and unquantized data for each demo. The synthesis repo, as cloned from GitHub, will already contain pre-trained and pre-quantized data. Similarly, the SDK submodule, which we visited previously, contains pre-generated C projects. This pre-generated content allows you to start at just about any point from training to synthesis to C code and immediately generate output. However, it's important to understand that by running scripts like GenDemos or the quantized scripts or the training scripts back in the training repo, you will be overriding pre-generated content. Working from the demo models and related scripts and resulting C projects is a good place to start, but you'll quickly want to start branching off into a customized workflow specific to your project. The recommended way of doing this is to start with a demo that best aligns with your goals, and then copy, rename, edit scripts, model definitions, and network definitions suitable to your product. There are a lot of details that become relevant during the process, and the readme.md files in the training and synthesis repos, as well as the Bash, Python, and YAML scripts themselves, are essential references.
Welcome back. So I'm going to show the same slide that we showed yesterday about the development flow. At the top, that was the material we covered yesterday, and it ended up with us starting to kick off a training run for our KWS-20 model. Below the bar, that's today. So we're going to take the generated output, convert the floating point into integer, into a checkpoint file, and then eventually run it through our tool we call the ISER that creates C code that you can finally run on your embedded device. So let's go switch over to the Linux command line. We're back here on the Linux command line, and you can see that our training run ended. You'll also notice it created a log file. Let's go take a look inside that log file. So I'm just going to mark that here. And then look at it. So we started at 16:08 and it finished at 18:11. So roughly 2 hours using that GPU, meaning that if you were running it on a system without a GPU, expect 10 hours plus for this run. You also can see how much better it got over time, and then at some point it plateaued. This is not specially set up for best results or anything. We just want to have something that finishes in time. So the top one of the verification set ended up being 84% or so. And the best one was 86. So we're going to choose that best. When you look at earlier in the log file, it started out here in the first one, started out at 47%. So it improved quite a bit in those 2 hours. In general, the log file is very useful to see what happened and where you might want to tweak your training or if you wanted to change parameters. It also, in regular intervals, creates checkpoint files so you can abort and resume training just in case you need to reboot or step away or need the machine for something else. Okay, so now we have in this directory 202101. Several files. The best and the checkpoint are the two that we're interested in, and we're going to choose the best. Now, even if you didn't get to train this network yourself, if we switch over to our other repository, we've provided a pre-trained version of that for you. Let's go to the synthesis directory. And again, making sure that we are current here, and we are. And when you look at the directory named trained, you will find an AI85-KWS20_V3-QAT8.pth.tar. That is the result of a training run, just like the one that I showed you. And we are also providing the log file that was generated with that run. So you can look at those. This checkpoint file still contains the floating point data. So it's straight out of PyTorch, and we haven't done anything with it. The next step that we need to do is to convert those floating point values into integers, because that's what our accelerator understands as integers for both data and weights. And for the weights, of course, we can do both 8-bit, 4-bit, 2-bit, and less. So now we could either copy our freshly generated checkpoint file from the training directory, latest log directory, and best to the current directory, or just for convenience, we can just use what's in the train directory, and that's what I'm going to do so that everybody will have these same exact results, because it may change from run to run depending on whether you are fixing your random numbers or whether you actually let them be random. So in the scripts directory, you will find a script that does this quantization step. So let me run that real quick. Scripts/quantize _ KWS 20 _ v3.sh. And that's all it did. It takes that checkpoint file, which was in the train directory, and creates a new checkpoint file, which will also place in the trained directory that is now quantized. And you see a little bit of a statistics down there, but really nothing special. Note that we did use quantization-aware training, so this is why this works so well. If we hadn't been aware of quantization during training, we would now have to go and look for a special scale factor and other things to get from floating point to integers without too much loss. But because of quantization-aware training, we don't have to do any of that. Okay, so we have our quantization-aware trained and quantized checkpoint file. And now we could go back to the training directory and evaluate it. You may have seen in the scripts directory of the training repo, there are scripts that are called evaluate _ something. So we're going to run scripts/evaluate KWS 20 _ v3. And that'll read in this new file that we just created. You can see here. If I scroll up, you can see it references AI8x synthesis /train /AI 85-KWS 20 _ v3-QAT8-Q.pth.tar. So, and what this does is it sets a switch in the training program to tell it that we are using integer weights and to behave exactly like the hardware. So now you notice the top one with this file is 82.4, which is less than what we had using our floating point in training. But this really tells you what the performance is and how much you lost during quantization. It's especially important when you're using 4-bit weights or 2-bit weights because the loss can be bigger. So you would, before going on loading this file onto hardware, you definitely want to make sure that the performance is still acceptable. And this is what the evaluation step is for. So I think we're done on the training side here. We did the evaluation. So I'm going to go switch back to my other window in the synthesis directory. And now the last thing to do really is to generate the C code. And of course, there are more scripts for that. So the script that we have here is called gen demos MAX78000, and it recreates all the demos that we ship. So let's just make a copy of that script and change it so we just generate one of the examples. So gen KWS 20 _ v3.sh. Edit that and get rid of all the other examples. All right, so that looks good. And it will place the output in the subdirectory SDK/example/max78000/CNN. So I'll just remember that and go there when we're done. Start this new script that we just made. And it shows you some statistics from that checkpoint file that we just made. And you can see there are 9 layers, 170,000 bytes roughly of parameters. It's using the KWS20 dataset, and it's called KWS20 v3. So it's generated, and we can go into SDK/examples/max78000/CNN/KWS20 _ v3. And you'll note there are bunch of C files, some header files, and a few project files. So at this point, you could hand this example, after you've tested it once in the hardware, you could hand that to a Windows developer. You notice there are some .launch files and other things that are Windows compatible. Let's just go take a quick look at what we have there in terms of structure. So you have a CNN.c and a CNN.h. Those contain the main functions and parameters for your neural network. And if you were to come up with a better model, or you were to retrain it and you would get better results, those are the two files you would swap out. The main.c file, that's really a wrapper file that's auto-generated just so you can get going. But if you are doing real software, that would be the file that you start modifying. You do real I/O and real processing. Of course, there's also a log file, which we'll take a peek at in just a minute. And then another file here that might be interesting, it's sampledata.h. That has one frame of a right-sized input, which we're using for a known answer test. So we can now compile this and load it on our device, and I'll show you what that known answer test looks like. After that, we're going to go back and examine how the tool converted our checkpoint file into the C code. Since I already have all the tools installed, C documentation, I can just hit make, and it'll build the example for me. Note it also will compile the library since that hadn't been done yet. And any minute now, it creates an output file named build/max78000elf. I've already got the debugger running. And again, if you use Eclipse, that's a single click. I'm just showing you on the command line, just in case. So arm, none, EABI, GDB, build, max78000elf, target remote 127.001:3333. So we're connected to the debugger and I can load. And as you can see, it's programmed in Flash now. And when that's done, we are just going to make sure, using compare sections, to make sure that everything is loaded correctly. And you can see it has. So now we're going to reset the CPU, monitor, reset, halt, and we can run it. And you won't see any output here in the debugger because the output will be on the serial port. So I'm going to go switch over to that serial port right now. And you can see it ran. And it says it passed, which is our pass-fail test, took 1.4 milliseconds, and these are the results for that one example that we gave it. So that really is what you get auto-generated from the tool. It's just a simple pass-fail test that makes sure that everything is working properly in hardware, and you should do that before you hand off your CNN to the embedded developers that will add all the I/O functions, because there's no point in trying it if there is something more fundamentally broken. So now we know the math is working, everything is good, and it runs on the device as expected.
I'm going to walk you through a quick way to start exploring the machine learning capabilities of the MAX78000. All you need is a Windows PC, an internet connection, a MAX78000 Featherboard, or EV kit. The first step is to download the Eclipse IDE and SDK toolchain. With that, you can compile pre-trained and synthesized machine learning demonstrations that come with the SDK. So what you'll want to do is go to maximintegrated.com and search for MAX78000. You'll see a list of all MAX78000 related resources, but what we want to get to is the MCU's main page. So select MAX78000 here and then design and development. You'll see links to each of the evaluation platforms here, but just scan down a little bit further to find the Maxim Macros SDK. This download contains all the software you're going to need. Click Download and select Maxim Macros SDK.exe. You'll need to create an account with MaximIntegrated.com and log in order to download the package. Since I'm an employee of Maxim, I have a slightly different path in. In any case, once you log in, you can download the package. Windows Defender may complain about the package because it's not signed. Just make sure you're downloading from MaximIntegrated.com via HTTPS, and it should be safe to run. Now we'll click through the installation wizard. I'm going to take all the defaults. The installer needs to download various packages online, and this process can take a while, so I'll just time warp us forward. And it's installed. Now find the newly created link in your Start menu called Eclipse Maxim SDK and launch Eclipse. Choose a workspace and done. Before we import our first demonstration project, let's take a short detour and explore the directory structure of the SDK we just installed. I'll navigate to the installation directory. In the documentation directory, you'll find an HTML document that references all the readmes in the SDK, library APIs, as well as some online resources. In the examples MAX78000 directory, you'll find all the example firmware applications. What you're likely to be most interested in can be found in the CNN directory. This directory contains examples that use the convolutional neural network accelerator in the MAX78000. The directory location is worth remembering because we'll need to reference it in order to import CNN examples into Eclipse later on. However, before I show you that, let's wrap up the directory tour. Back to the root of the installation, we'll find the libraries directory. This contains board-specific ARM Synthesis and MAX78000 peripheral driver code. So those are the top three directories you'll want to be aware of. Now let's go back to Eclipse and import a CNN example. Let's do a File, Import, click General, and Existing Projects into Workspace. In this dialog, we'll need to specify the path to the CNN directory we visited earlier. And now we see the CNN example projects. I prefer to have files in my workspace, so I'll click this and select Finish. Give Eclipse a little time to chew on that, and now we have all the CNN projects loaded into Project Explorer. So now let's compile KWS-20 demo, which is a 20-word keyword spotter that was trained with Google's speech command dataset. By the way, you'll see that we also have a KWS project. The difference between the two projects is that the underscore demo version is a full demonstration of keyword spotting, while the KWS-20 is simply a known answer test, meaning that audio data is embedded into the C code to serve as a known answer test for validating CNN inference. Therefore, you don't need a microphone. I'm going to right-click KWS-20 demo and build. Now, one thing to be aware of is that the demos are by default configured to run on the EV kit. If you're using a Feather, you'll need to go into the Makefile and make sure this board equals definition is set to Feather Rev A. This board equals EVKit v1. That's how it comes out of the box. So make sure you comment that one and uncomment that line so that your target's a Feather board. Then you'll be good to go. So now we're ready to debug. So the first time you debug a project, you're going to have to come to Debug Configurations, open up GDB Open OCD Debugging, and all the projects should be listed here. Select yours, just accept all the defaults, and you can start a debug session. So it's programmed to chip right now. Once it's done, we should get a breakpoint on main. And there you are. The KWS-20 demo outputs keyword spotting results to the USB UART that is implemented in the USB interface connected to the host PC. I use PuTTY to connect to the UART, but any terminal program should work. So let me run up PuTTY, and I already have a configuration made. So I'll load that up. And this is the output from the KWS-20 demo. So it's hearing me talk. It doesn't know what I'm saying most of the time, and it's guessing. So let me go ahead and say a few words that I know it understands. Up, down, left, right, 1, 2, 3. Small batteries are a common feature of embedded AI products, and the MAX78000 was designed to enable extremely power-constrained applications. We've talked previously about the CNN accelerator architecture, which makes applications like keyword spotting and Face ID possible on a small battery. And now I'd like to take a brief look how the goal of energy efficiency impacts development workflow. Broadly speaking, energy efficiency involves 3 aspects. The first is pretty obvious, and it isn't specific to the MAX78000 or even embedded AI applications in general. It's a common theme to most embedded devices that run on a battery. I'm talking about the balance to be struck between the feature set, battery capacity, and by extension battery cost, and battery longevity, that is, the time between charges or replacements. The next aspect to consider is a concern primarily for the machine learning guys. That is, minimizing inference time. The less clocks required to perform an inference, the lower the power cost will be. This goal is attained by first choosing the right model for your application. A wrong choice in the beginning can yield results that no amount of tweaking later in the workflow can solve. A general rule for ML initiates is to go with what has already been proven to work. In addition to initial model choice, you need to be aware of how well and even if a particular model can be realized within the constraints of the MAX78000's CNN. This means that having a working understanding of the CNN architecture is important during model development. Constraints concerning the maximum model size and structure, as well as the number of required weights and weight resolution, all need to be considered. The final aspect of energy efficiency is that of minimizing processor clocks, which is of interest to the traditional embedded software folks. This means sleeping where possible, that is, turning off the Cortex via WFI, for example. When it's time to do something with the CPU, then do it as fast as possible. Downclocking the CPU generally doesn't yield the best results. Part of CPU clock minimization involves paying special attention to time spent dealing with I/O. This can often be the most inefficient part of the design. Reducing CPU involvement with I/O handling is often key, and you may want to take advantage of DMA-enabled peripherals as much as possible. The RISC-V core can also be leveraged to serve as a smart DMA engine, but in our experience the RISC-V does not contribute much in the way of energy savings unless its operation can be pipelined with Cortex and CNN activity. Generally speaking, if you need to burn CPU clocks, the Cortex is the best option due to its substantially higher clock frequency. This is just a rule of thumb though, and you may find innovative uses of the RISC-V core in your application. So I wanted to step you through exactly how you'd go about measuring inference time on the Feather, or really any time period. So I've loaded KWS20_demo, and I'm looking at main.c. And you'll find in here, we start a timer, we perform some operations, and then we read out the timer value, and we print that out to the display. And that's going to print out in microseconds how long between this point in the code and this point in the code. And so what's going on here is we're starting the CNN, which has already been loaded with data and configured, and waiting for it to complete. Then we're unloading the data, and that's the time period of interest right in there, and that's what we're printing out on the screen. So we can go ahead and I'll use PuTTY to open, let's reset that. There we go. Left. Okay, so here's the value being printed out, and you can see that that time period is approximately 2.6 milliseconds. Now, measuring inference time and other periods of time associated with CNN activity can be useful for tweaking your model. Just an iterative process of trying and seeing what the results are, working towards a minimized time period for the CNN. And this is the quick and easy way of obtaining feedback for optimizing your model for power consumption. But it doesn't measure power directly. For that, we have another tool that I'd like to show you.
This is the MAX78000 EV kit. As you can see, the kit is a lot larger than the Feather and has a few more features, like a color TFT and an integrated microphone. Now, I've taken the TFT off because the backlight was interfering with my camera I'm using to take this footage, but it's not relevant to the feature I want to show you. The circuit has a power monitor right here, and it measures voltage and current of all the MAX78000 supply rails and prints that information to this LCD and outputs and logs it to the USB UART here. So as you can see here, it's measuring average power of all the rails, DDB, CA, CB, and RA. And we can use these buttons to navigate to different modes. So we have a CNN power mode, which I'll show you in a minute, system power mode. And then we have sort of digital multimeter type functionality. We can measure the voltage of each rail, the current of each rail, and power for each rail. And you can see if I put the board into reset, you'll get different power figures. Bring it out. I'm going to show you CNN power mode.
The power monitor works in cooperation with the synthesizer, AI8exciser.py. You can tell the synthesizer to output profiling code with the -- energy option. This profiling code enables the power monitor to measure power at specific points in time, like data loading, loading of weights, and of course CNN inference.
So let me show you what CNN power mode does. I'm going to reset the firmware, and it's going to profile different areas of the code. Idle power, kernel loading power, input loading power, input inference. And then it gives us a set of values. The top number is energy, so 134 microjoules. The next line is T, which is time. The measurement period was 11.5 milliseconds. And then idle power of the measurement was 6.26 milliwatts, and active power during the measurement was 17.85. And so we can look at the kernels, kernel loading, input inference. Now all this data and all these modes are detailed in an accompanying document, but I just wanted to quickly show you that for those who really want to drill down and obtain maximum power efficiency from the device, we have a tool for that, and eventually you're going to want to get your hands on this kit.
On behalf of myself, Sean, Robert, and Maxim Integrated and EBV, I'd like to thank everyone for listening to our webinar. Hopefully everyone learned something about working with the MAX78000, and we've given you tools and the direction that you need to start working on your own projects. Personally, I can say I've been very excited by the market reception to the MAX78000, and extremely excited by the creativity that we're seeing from our customers. What we're seeing is that because we can make vision and hearing something that can be so low power, they can run it on a small battery. We just see a whole universe of possibilities opening up, and we're very excited to support those possibilities. So this concludes the prepared portion of session number 2, and now we'll move into a live Q&A. Thank you.